Section 14.2, Limits and Continuity. Let f be a function of two variables whose domain D includes points arbitrarily close to a point AB. Then we say the limit of f of xy as xy approaches AB is L, and we write the limit of f of xy as xy approaches AB equals L. If for every number epsilon there is a corresponding number delta, such that if xy is in our domain D and the distance, which is what this is, between xy and AB is less than delta, then f of xy minus L, the distance between those two guys, is less than epsilon. Remember that in single variable calculus, we talked about how the limit would exist if the absolute value of x minus a was less than delta, because we're saying that x would get close to a, the distance between x and a would be less than delta, then that would force the distance between our f and our limit to be less than epsilon. But in 3 dimensions, we have to use the distance formula in 2 dimensions, because our domain is not just on the real line, the domain is R2, it's in 2 dimensions. We have x and y values as inputs. So we just adjust our definition for our limit a little bit. However, this causes a couple of different issues in 2 dimensions. Let's say we had some function somewhere and we're looking at the limit at, let's say, a. So then we would look as we approached from the left and as we approached from the right, and we would see if the values of the function would match up. And then if they did, then we would say that those values were the limit of the function. However, in 3 dimensions, our domain is not just a line. Our domain is in 2 dimensions. So we're not just restricted on the left and the right. We could go from above, well, not really above, but you have to think about it in terms of a little perspective, where you could go from any different direction. So not just left and right, is just the point I'm trying to hammer in here. Not even just that, but if you go from the left, there's only one possibility: you go along a line. If you go from the right, again, you can only go along a line. But in this case, I could come in from the left, but I could wiggle around, because I'm in my domain. Let's say that this is the domain. It's in 2 dimensions. So I don't just have to approach via a line. Even if I come in from the left, I could wiggle around first and come in, or I could come in this way and then down, or this way, whatever. So there's not only tons of different directions you can approach, but there's tons of different paths as well, because you can do so much on the path even as you approach from a certain direction. So there's a lot more possibilities of approach here in order for us to say that our limit exists. So we can't just check left and right, we have to check basically an infinite number of different directions all at the same time to see if a limit exists. However, the one advantage of this is that it's very easy to see when a limit does not exist, because if we approach via one direction and we find any of those infinite other directions approaches and gives us a value that doesn't match, then that's it, our limit doesn't exist. So as an example of that, let's look at the limit of x squared minus y squared over x squared plus y squared as xy approaches 0, 0, the origin. So to show that this doesn't exist, how about we first set f of xy equal to what we're taking the limit of. So x squared minus y squared over x squared plus y squared, and let's choose a couple different paths to approach on. So how about we go along the x-axis first? So that would be if y is equal to 0. So if y is equal to 0, then instead of writing f of xy, I could write f of x0 because I'm plugging in 0 for y. So that leaves us with just x squared over x squared, because the y's disappear. Well, that's just 1, provided that x is not equal to 0. So that means that f of xy approaches 1 as xy approaches the origin along the x-axis. So how about we next go along the y-axis? We'll set x equal to 0. So now we look at f of 0y, because we plug in 0 for x. So that's minus y squared over y squared, which is minus 1, provided that y is not 0. So that implies that f of xy tends to minus 1 as xy approaches the origin along the y-axis. Okay, so we just got two different values for our limit with two different approaches. Remember, in both cases, we're still approaching the origin 0, 0, but they don't match. So there's no way our limit exists. So we'd say the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist, or DNE. Let's do another example. How about if we have the function xy over x squared plus y squared? Again, we will approach the origin. So how about we go along the x-axis again? So that's where y is 0, so we're looking at f of x 0, and we get 0 over x squared, which is 0. So it looks like f of xy approaches 0 as xy approaches the origin along the x-axis. Okay, let's check the y-axis now. So we have x equals 0 again, and we look at f of 0y. So that's just 0 over y squared, which is 0. Okay, well now these guys actually match. We have f of xy approaches 0 as xy approaches the origin along the y-axis. So maybe this time our limit is actually 0. But we have to be a little bit careful. We only checked two paths. Remember, there's infinite different paths that we could approach 0 on in 2 dimensions. So how about we check the line diagonally? What if we zero in on y equals x? So we travel along y equals x. That means that I have f of xy, but y is equal to x, so I just replace that with x, do f of x. So that would be x squared over x squared plus x squared, which is x squared over 2x squared. So I'll cancel out the x squareds and just get 1/2, provided that x is not 0. So that means that f of xy approaches 1/2 as xy approaches the origin along the line, the diagonal line, y equals x. So if I just write y equals x. Okay, well, we got two different values. We got 1/2 along y equals x, and we got 0 along this other path, so limit must not exist. That's it. So we'll write the limit of f of xy as xy approaches 0, 0 does not exist. If f of xy equals xy squared over x squared plus y to the 4th, does this limit exist? Well, how about we save a little time? Instead of going along the x-axis and along the line y equals x, how about I just do every single line through the origin at the same time? So we could write lines to the origin. Remember, that's mx plus b for a line, so b is 0 if my y-intercept is 0 through the origin, so this is just y equals mx. So I'll set that to be my path and accommodate for all of our lines at once. So we're looking at f of x and then replacing y with mx. So that's just x times mx squared over x squared plus mx to the fourth, which is m squared x to the third over x squared plus m to the fourth times x to the fourth, and that's m squared x over 1 plus m to the fourth x squared. So let's take this to 0. We get 0 over 1, so it looks like this thing goes to 0. So we could say f of xy tends to 0 as xy tends to the origin along any line to the origin y equals mx. The only issue is that this does not accommodate for undefined slopes. In other words, it doesn't accommodate for a vertical line, the y-axis, so we'll have to check that separately. So let's do that. If x equals 0, then we're looking at f of 0y, which is just 0 over y to the fourth, which is 0, so it looks like it's still 0 over there also. So any way we approach the origin, as long as we approach on a line, it looks like our limit would be 0, because we just did an arbitrary line y equals mx to the origin, and we just showed it for the y-axis. However, remember, just because we approach from all these different directions and still hit 0 doesn't mean that the limit is 0, because even when you approach from different directions, it's possible to approach from different paths. So what we showed is that if I approach like this, or I approach like this, or I approach like this, or I approach like this, then the limit is 0. But I didn't show was if I wiggle around that the limit would still be 0. So that's what we have to do next. How about we test some other paths? Well, if you run out of equations that are linear, your next step would probably be try some quadratic. So how about we try a parabola? Let's let x equals y squared. So that means that we're looking at y squared instead of x, so I'll replace that, and I'm taking f of y squared y, so that's just y squared times y squared over y squared squared plus y to the fourth, and that's just y to the fourth over 2y to the fourth, which is a half, assuming that y is not 0 and all that. Okay, so that means that f of xy approaches 1/2 as xy approaches the origin along the parabola x equals y squared. So again, our limit does not exist. I mean, at this point you might be asking yourself, hey, are we ever going to do a limit that does exist? And we will, but it's, like I said, much harder to see if a limit does exist with all these variables, because you have to accommodate for every single possible path and direction at the same time. So in order to do that, what helps a little bit is having some limit laws. The limit laws that we did in section 2.3 can be extended to functions of two variables, where we have limit of a sum, sum of limits, limit of product limits, so on. And we can also have the limit of x is just the a value plugged in, limit of y is just the y value of the point plugged in, and the limit of a constant is just the constant. And we have the squeeze theorem. So we have a bunch of helpful results that we won't bother to prove. So let's do an example and see if this limit exists. So we could try approaching from a bunch of different directions. If we approach along the line y equals mx like we did last time, we should see that this thing will tend to 0. We could also see that along the y-axis, y equals x squared, x equals y squared. So it makes us think, okay, well, we did a bunch of different paths. Maybe the limit actually is 0. So let's just get that out of the way. We have 3x squared y over x squared plus y squared. And I'm not going to show it, but you could pretty easily. But this thing will tend to 0 as xy approaches the origin along y equals mx, the y-axis, y equals x squared, x equals y squared, and just about any other path you could think of, because it turns out that this limit actually is 0. But we have to actually justify that somehow. So we can either use some limit laws if we can think, or we can just go back to the definition. So let's try using the definition first. We'll let epsilon be some positive number. In order to apply the definition to show that the limit exists, we want to find some delta such that if the distance between x, y, and 0 is 0, so that's just the square root of x minus 0 squared, which is x squared, plus y minus 0 squared, which is y squared, is less than delta, then that should force the distance between our function and our limit to be less than epsilon. So our function is 3x squared y over x squared plus y squared. Our limit is 0. We want that distance to be less than epsilon. So this is the same thing as saying that the square root of x squared plus y squared is less than delta. Then this, let's see, I can just take the absolute value of 3x squared is just 3x squared because it's all positive. Absolute value of y will have to stay absolute value of y, and our denominator, again, x squared plus y squared is always positive, so don't need the absolute value of it there. And then minus 0 is just nothing, so we just need to show that if this is true, then that forces this to be true. Okay, so how about we manipulate this a little bit so that it starts looking a little bit more like this? And that'll give us a candidate for our choice of delta. So notice y squared is always greater than or equal to 0. So that means that x squared is always less than or equal to x squared plus y squared, because I'm adding something to x squared, and what I'm adding is greater than or equal to 0. So this must be greater than or equal. It must be at least as big. Okay. Well, that means that if I have x squared divided by x squared plus y squared, then that must be less than or equal to x squared over x squared, which is 1. Because if you're dividing by something, then you reverse your inequality. Okay, so that's pretty cool. That means that if I look at 3x squared times the absolute value of y over x squared plus y squared, that must be less than or equal to 3 times the absolute value of y, because this entire thing must be less than or equal to 1. Okay, well, this is the same thing as saying 3 times the square root of y squared, which is less than or equal to 3 times the square root of x squared plus y squared by the same logic as before. I'm adding something inside over here, which is greater than or equal to 0. So it must make this thing bigger. Okay, so this is very close to this. In fact, if I were to set this less than delta and divide by 3, it looks like, or less than epsilon divided by 3, it looks like I should choose delta equal epsilon over 3. So let's do that. Okay, and now let's test this. If the distance between our x and y and our origin is less than delta, then we'll have 3x squared y over x squared plus y squared minus 0 is less than or equal to 3 times the square root of x squared plus y squared, as we showed. But we're assuming that this thing is less than delta, so that makes this less than 3 delta. But we chose delta to be epsilon over 3, so that means that this is 3 times epsilon over 3, which is epsilon. Okay, perfect. So we just found a delta that forces this to be true. So that means that our limit actually is 0. So maybe I should have written a bit smaller, but I could say the limit of our function was it 3x squared y over x squared plus y squared actually is equal to 0. Okay, a function of 2 variables is called continuous, pretty much the same way that a function of 1 variable was continuous. The limit of the function has to be equal to the value of the function. So we say that f is continuous on a domain D if f is continuous at every point AB inside of that domain D. Then we have a definition of a polynomial of 2 variables, pretty similar to a polynomial of 1 variable, except that you just have another variable in there multiplying each of the terms. And then a rational function is just if you take 2 of those polynomials and divide them. So what we can do is use the limits in the remark that we had before to show that the functions f of x equals x, g of x equals y, and h of x equals c are continuous. Since any polynomial can be built up out of the simple functions f, g, and h by multiplication and addition, it follows that all polynomials are continuous in R2. And any rational function is also continuous in its domain because it's a quotient of continuous functions. By the way, if we go back to remark 2 for a second, notice we said the limit of y was b. So in fact, what we could say over here, instead of going through our epsilon-delta proof, was after we got to this point, the limit of 3 times the absolute value of y as xy approaches 0, 0 is equal to 0. This says that you can just plug in if you have just 1 variable. So that means that we have this thing, when we take the limit as 0, this thing is greater than or equal to 0, so by the squeeze theorem, this limit would have to be 0. So that's an alternative way of approaching this problem over here. Alright, let's take advantage of a couple of the things we just talked about to evaluate some limits now. Notice this thing is a polynomial. So write that f is a polynomial. And we just said that all polynomials are continuous, so this means that f is continuous. Since it's continuous, the limit must exist and equal the value of the function. So that means that I can find this limit just by plugging in, so that's wonderful. We'll get the limit as xy approaches 1, 2 of x squared to y cubed minus x cubed y squared plus 3x plus 2y equal to 1 squared times 2 cubed minus 1 cubed times 2 squared plus 3 times 1 plus 2 times 2. So we love polynomials because we can just plug in. Okay, how about this function? Let's see where that's continuous. Notice that f is undefined at 0, 0 at the origin, and f is a rational function. We just said that rational functions are continuous on their domains. So that means that f must be continuous on its domain, which is just where it's not undefined. That's where it is defined. So that's all of the points x, y, such that x, y is not equal to the origin. How about this function over here? Well, notice this is a piecewise function. Our issue before was that f was rational, but it was undefined at the origin, but now it is defined at the origin, because we set it equal to 0 there. So let's see if it's continuous. Well, we need to take the limit of this guy. So the limit of g of xy as xy approaches 0, 0. But we did this already. This is the same function that we did in example 1. So we showed very quickly that this limit does not exist. So that means that even though it's defined there, g is discontinuous at 0, 0. But we said that it's continuous on its domain for the rational part of this piecewise function, so it's continuous elsewhere at least, as it was before. So just because you fix a hole in your function doesn't make it continuous, as we saw in single variable calculus. It matters where you plug the hole. If f is a continuous function of two variables and g is a continuous function of a single variable that is defined on the range of f, the composite function is also a continuous function, h equals g of f. Before we use that though, let's keep looking at this example a little bit more. Let's see if we can find some way to make this thing continuous. Notice that f is continuous for xy not equal to the origin. And by the way, I've changed our piecewise function a little bit. This is not exactly the same as what we had before, but I think it would still be good to see a piecewise function where we actually do have some continuity. So this f is continuous for xy not equal to the origin because it's a rational function, at least in that piece. So because it is a rational function, how about I'll write there, it's just over here. And let's take our limit now. Well, we're looking at the limit as xy approaches 0, 0 of f of xy, and that's the limit of this thing, 3x squared y over x squared plus y squared. And hopefully that looks pretty familiar because we just spent all this time showing this limit exists and is equal to 0. We did that in example 4, so 0 is the value of the function at 0 because that's where the hole is plugged in over here. So perfect. That means that even though it was undefined for this piece, it's defined overall and the limit is equal to the value of the function, so f is continuous at 0, 0. And since it was continuous elsewhere due to being rational, it is continuous everywhere. So it's continuous on all of the R2, the entire plane. Where is the function arctangent of y over x? So we'll use h of xy to be that, and we'll rely on the remark we just mentioned about composite functions being continuous. How about we find a way to compose these guys? Let's set f of xy equal to our inner function, y over x. Notice that's a rational function. Okay, how about, well, rational functions are continuous everywhere in their domains, so f is continuous for everywhere that x is not equal to 0. Okay, how about our other outer function, so arctangent, so that's of a single variable, so let's use t. So arctangent of t, we know from single variable calculus, is continuous everywhere. So that means that our composite function, g of f of xy, which is arctangent of y over x, and by design that's our original function, h of xy, is continuous for everywhere except where x is 0. Okay, lastly we have the notation. The limit of f of xyz equals L, where xyz approaches ABC, means that the values of f of xyz approach the number L as the point xyz approaches the point ABC along any path in the domain of f. So basically we're just extending our definition of the limit for functions of 3 variables. Obviously we can't visualize this in the 4th dimension, but we can at least visualize the domain. And also we know how to extend distance formula to multiple dimensions. So we just take the distance between xyz and our point ABC, we make sure that that's less than delta, and that forces the distance between our f value and our limit to be less than epsilon. And then it's continuous, for the same as before, if the limit of the function is equal to the value of the function. If f is defined on a subset D of Rn in general, then we can define the limit in general the same way. We just remember we use this notation to say a whole bunch of variables, n variables, and we're plugging that in. So we say the distance between those n variables, the point at those n variables and our point at A of another n variables is less than delta, then that has to force f of the x values variables minus L to be less than epsilon, and if it does, then our limit exists, and then our function is continuous, same as before, if the limit of the function is equal to the value of the function.